we actually observed fluid flowing through the Bernoulli apparatus, and we can measure the diameters of some of those tubes. Like one of the tube has a diameter of 1.2 centimeters, the other a diameter of 0.88 centimeters. We're talking about inside diameter, okay, the diameter inside the tube. As water flows through the tube, assuming that the tubes remain full, which is pretty much the case, as we've seen, if you observe the system carefully, the tubes remain full. This one certainly remains full, and unless we're very near the end of this one and with a fairly low velocity, this one certainly remains full. The amount of fluid flowing past a point in the first tube, the larger tube, in a time delta t, is going to be V1 delta t, where V1 is the speed of the fluid in that tube. If V2 is the speed of the fluid in the second tube, then a volume V2 delta t will flow past a given point in this tube in time delta t. Actually, the volume is not V2 delta t. The distance the fluid flows here is V2 delta t. The distance the fluid flows here is V1 delta t. Okay, so let's clarify that. Moving at velocity V1, the fluid here will flow a distance V1 delta t. Moving at velocity V2, the fluid here will move a distance V2 delta t. Now, the volume, capital V1, and the volume, capital V2, are going to be related to the velocities, small v1 and small v2, in this manner. If we think about it, the amount of fluid flowing past a point here is going to be a cylinder, and the altitude of that cylinder, if you wish, and you think of the cylinder being turned on its side, is going to be the V1 delta t, the distance, and the cross-sectional area is just the cross-sectional area of the tube with this diameter. Similarly, here we have a cylinder whose altitude is the distance V2 delta t, and whose base area is the cross-sectional area of the tube of diameter 0.88 centimeters. Then we can say that the volume flowing through tube 1 is the area of the base of the cylinder, which is pi times r1 squared, multiplied by the altitude, which is V1 delta t. R1 here generalizes the 1.2 centimeter diameter that we observed. R2 standing for the 0.88 centimeters here, but really generalizing it. We see that the volume V2 of fluid passing a point here in time delta t is going to be pi r2 squared times V2 delta t. Now the key is that if these tubes remain full, the volume flowing through this tube in a given time is the same as the volume flowing through this tube in a given time. More specifically, the volume of fluid passing a given point in this tube during time delta t is equal to the volume passing a point in this tube in time delta t. So that the volumes V1 and V2 that we've calculated here have to be equal. Now the reason for that is that if the volumes weren't equal, then fluid would be accumulating someplace, provided if this volume is greater than this. And if this volume is greater than this, the fluid has to be coming from someplace other than here. And that doesn't happen. There's no buildup of fluid. We don't get extra fluid into the system. Whatever's there is there. So, noting that the volume V1 has to equal the volume V2, we write this as an equation using the expressions for V1, volume V1 and volume V2. Set these equal, we can divide the pi into both sides, and we can divide delta t into both sides, obtaining r1 squared V1 equals r2 squared V2, which tells us that V2 over V1, if we divide both sides by V1, and then divide both sides by r2 squared, is going to equal r1 squared over r2 squared, which is r1 over r2 quantity squared. This tells us that the ratio of the velocities is inversely proportional to the square of the ratio of the radii. The larger radius is going to have the smaller velocity, which is, of course, what we expect. The continuity equation, in general, tells us that the volume of fluid passing a point in one tube is the same as in the other. A1V1 is just the area of the base of that cylinder times the velocity. A2V2 is the area of the base of the cylinder in tube 2 times its velocity. Now that V is a little bit big. It almost looks like a capital V. It's still velocity, not volume, although it looks a little bit strange. The ratio of the volumes is the same as the ratio of the velocity is inverse to the ratio of the areas, and that is expressed in this equation here. And this is all related, so everything here ties together and tells us that it all follows from the assumption that the volume of fluid passing a point in one part of the pipe is the same as the volume passing another point. And again, these are really, if you multiply this by delta T, you get the volume. So this is just the equation that we started with up at the top here, but with the delta T canceled out. So this is called the continuity equation, very important in applications to fluid flows.